Okay, so hopefully you've seen this video, enjoyed it. So the reason for the experimental observation, a good explanation at least, in my opinion, is that we are occasionally along the line of sight of this jet that is emitted here, and occasionally, so somewhere oriented along this circle. And every time it sweeps over us, we see the signal. So here basically the rotational axis, the magnetic and the geographic north pole or poles are not aligned. With the Earth, it's I think 4% seen from us about 4 degrees that the magnetic north pole is next to the away from the geographic one. So we are at the moment just in the special phase and relatively lucky. Or at least previous people were lucky that needed a compass. But when I have seen this video, I was asking me a couple of questions. Well, first of all, why do the neutron stars spin? Why don't they collapse under gravity? Or what keeps them now stable? Why there is no the gravitational inward pull? What works towards the outside? That we have the gravitational force going inside, and in order to have a equilibrium, you would need a force working to the outside. Usually would introduce the centrifugal force, which is a wannabe force that's needed occasionally. But why is it not completely collapsing? And here on the outside, it would be, we would have to move the stuff faster, and then the inside less fast. So something has nothing to do. Well, where does this magnetic field? Oh, there are obviously magnetic fields involved that basically accelerate the particle beam out here. If you have a charged particle and there is one field line, what will happen? It's so-called Laurent Force. It will trap this particle and make it gyrate around, so rotate around this field line. Now, if we have a region with a high field line density and low, high field line density means usually a state of high energy, and the charged particle wants to be in the region with lowest energy, which is in the low field line region. So that would provide a mechanism to accelerate it. And then if a charged particle is accelerated or deaccelerated, it emits usually so-called Bremsstrahlung. At latest, when it's deaccelerated, it transforms kinetic energy into radiation, which would then produce light. So we would then basically have some kind of jets produced. But therefore, we would need a magnetic field. Where does this come from? Now let's go through these questions and learn a bit about neutron stars or pulsars, which are rotating neutron stars. Well, first of all, we have learned the neutron star comes from the gravitational collapse of this iron core. So it basically becomes very small, then bounces a bit back, and at some point it's just a neutron star left. Then we also remember that our very initial gas cloud had a rotation. It contracts and contracts and contracts, but this rotation still stays there. This angular momentum is preserved, which means the star also needs to rotate. Indeed, our sun also rotates. Like we rotate around about the intrinsic axis, our star does also. Most stars rotate. And now, if you have the figures, when this core contraction happens, so the core was then also rotating. And now when this core contraction happens, it's the same as with the figure skater. What changes? The mass distribution towards the rotational axis, which is given by omega, the angular velocity. The velocity, the angle is the change of angle with time, multiplied with this mass distribution. Mass multiplied with r squared, or integral r squared dm, infinite small mass element. This gives us a so-called moment of inertia. Well, this product defines us again the angular momentum. Now we make the mass distribution smaller. Since this is constant and we make I smaller, omega has to increase. Therefore, the change of the angle with time increases. The angular velocity, the rotation itself becomes faster. Oh, the same mechanism is here in place. So a star which might rotate relatively slow, and now so at least at the core, which should then rotate relatively similar with a similar velocity. Otherwise, we get there again friction in the different layers. So we would assume that the core rotates similar velocity, same velocity as the star, but then it drastically contracts and starts spinning much, much faster. So that would explain us already why these neutron stars can spin so fast. There are a couple of them, they are relatively fast. If you remember a radius of 12 to 14 kilometers, and now you build a roundabout in the playground, 12 to 14 kilometers, so that it rotates once around the circle in 1 second, that would be 1 hertz. You would probably puke. Honestly, if I'm now going with my son on the standard roundabout, I'm already close to, or with the age, you really, Well, the fastest that we have observed so far is this PSR J1748 minus 244680, whatever this means. The frequency, it has, so this also known as this Velar pulsar. Somehow it sits in here, then we have again gas that is obviously infalling and start shining. And we see here something coming out. It's obviously glowing matter, it's hot matter. This is obviously related to the jet. So here we nicely get the rotational, where the rotation happens, as well as the direction. So that seems to be relatively stable and not, there seems to be the rotational axis and the magnetic pole aligned. Otherwise, this jet would be going around here in a circle. And we would, instead of a disk, we would observe some lentile shape, discus-shaped object, or a bigger, more extended, maybe even spherical. And this has a frequency of 716 hertz. 716 rotations per second. Even a small object that spins with 716 is the music that would be already a sound. So it's something that we nicely could hear already with quite a good frequency. So our sound, I think, is between 50 hertz and 1500, I think. I would have to check this up again. Okay. Interestingly, we know where they have been made, usually in the center of these nebulas. And sometimes they can even, in this explosion, obviously the explosion is not happening spherical. It gets some direction that maybe the matter is ejected on one side and the remnant, what is the neutron star, on the other side. There's one found in this lighthouse nebula. Nice word for this pulsars. Or near the lighthouse nebula, which is a so-called runaway pulsar. So here's the nebula, the supernova remnant, and somewhere nearby we find this runaway pulsar. But we have to look here with X-rays in order to find the pulsar. But this was flying with a velocity between 0.3 and 0.8% of the speed of light. 3,000 kilometers or 1,000 kilometers per second. In 40 seconds once around the Earth. So sometimes they're pushed away, depends on the dynamics of the explosion. But the interesting thing here is that they often rotate. In general, so normal pulsar would have a frequency of maybe 1 Hertz. That means every second you get this signal. And if you remember, this was named Jocelyn Bell, this was 1.3 seconds, so a bit less than 1 Hertz. Oh, we have already understood something, not too bad. So the fastest rotating one, and then how can it be that the majority, well, usually when you rotate and you emit some radiation, the radiation needs to come somewhere from, it's usually taken out of this rotation. So it slows down with time. But sometimes they even seem to fast speed up. This can happen if they are in a binary. You know, the other star extends somehow a bit over this Roche loop, which must be from the center of gravity, obviously very close towards, closer to the smaller star compared to this massive object. So it might start now nicking material. What we then get is again this inspiraling gas. It needs to inspiral perpendicular towards the rotational axis because of this angular momentum. Inspiral means that there must be collision between the gas, where one gas molecule gives the other, or gas dust grain gives the other dust grain some angular momentum. Or in the collision, it loses a bit of velocity, can go to the inside, while the others is getting some velocity, gaining velocity, push towards the outside. So one gives angular momentum to the other. And then slowly but surely the stuff falls in. And now, of course, it will come already perpendicular. This is now in the roundabout when you want to speed them up. You have to push alongside. If you push alongside as the stuff is coming in, you accelerate the roundabout. So they can increase when they start feasting and eating stuff. They basically increase their velocity. It's speeded up, and therefore the frequency gets shorter, higher, or the time interval between two observations becomes shorter. So we have basically clarified the two mechanisms. First of all, the initial star had some kind of rotation, and second of all, infalling materials, usually bringing angular momentum and pushing everything on. Question 2. Why don't they collapse under gravity? What we observe in nuclear physics is that Normal nuclear matter tries to have distances between proton, neutrons of 1, 1.2, or proton, proton, neutron, neutron, between nucleons of, so roughly a femtometer. That's about also the mean square charge radius of the proton. 10 to the minus 15 meters. If we come up, but if we come now to try to squeeze them together, the energy, potential energy goes up because they start now repulsing each other. And this is coming from the substructure. This is what we call a hard core, that we cannot merge them completely. It is coming from the substructure because we have here now again quarks. There are buildup of these quarks. And these quarks are again the spin half particle, the so-called fermions, like the electrons, these loaders. They are subject to the so-called Pauling principle. And the same statistics applies. They cannot be, if they have the same velocity, the same angular momentum, the same spin, they cannot be in the same place. Pauling. That means they need to repulse each other. So we cannot squeeze them together below a certain limit. This is again this degeneration pressure that works also for the electrons. This works again against the gravitational collapses. The maximum mass that this can work. This is now called the Oppenheimer-Volkoff limit, but it's essentially similar to the Chandrasekhar mass. So it's always when we have these loaders, they do not want to go together too well. And it's again this degeneration pressure that stabilizes the system against further collapse. Sorry, I made the mistake last Sunday. I went with my son a bit of walking and then we got trapped in the wind and rain and whatever, and had to walk home. But of course I first sheltered the boy. So now we qualify, but obviously with the electrons we have seen, there is an upper limit. And here it's this Oppenheimer-Volkoff, which I think was 2.07 times the mass or solar masses. And then we would get further gravitational collapse. Now, recently there was an observation that was a neutron star that was heavier. But if it rotates fast, there might be a limit, or that this limit is taken a bit down or can be raised, because now we have also the centrifugal force working towards the outside, reducing the pressure a bit. Brings us to the next question. Where do this magnetic field comes from? Well, first of all, what is the source of a magnetic field? Usually the source of a magnetic field is a current. Charges that change, or a flux of charges, charged particles, along a conductor. And then we will see this is surrounded in concentric circles by a magnetic field. The field lines are then defined as what is called the right-hand rule, that we take the sum in the current direction, but this is now the electrotechnical current, which is opposite to the physical current, or for positive charges. So, but in the moment we have a current, some charge is flowing, we get this magnetic field. But now we have a problem that basically everything that we have, all these 95% of the stuff, are neutrons. Are they charged? No. Per definition, the name says already neutral, neutron. Yet again, what comes in, but this is very interesting stuff. They have this substructure, up, down, down quark. In fact, the down This the first indication that they need to have a substructure, proton as well as neutron, was their magnetic properties, because they are now made up of charged particles, which somehow need to flow around there. A quantum particle needs always to be in motion. That is basically Heisenberg's uncertainty relation. You need to have uncertainty in space and uncertainty in the momentum or velocity that is larger than Planck's constant divided by 4 pi. So if it would be addressed, the uncertainty in the space would be 0, and therefore the uncertainty in the momentum would be infinite. Therefore we would have infinite fast quarks, and they couldn't be bound anymore. But there would be infinite fast, but it's of course that they are at rest. This is a contradiction. So this is not possible. So then they always need to be moved with a bit. And when they move, they are charged, they make a magnetic field. This magnetic field will then interact with an external magnetic field with a certain strength. So we would call this property, this magnetic charge of the neutron as well as the proton, we call them, electron the same, we call them a magnetic moment, which is essentially telling us this is a source of some elementary magnetic field. This is characteristic for each elementary particle that is charged or build-up of charged particles. And since the neutron, there was this magnetic moment observed. Don't want to know how the faces looked like when the experimentalists did the experiment. At this time, I think must have been Isidore Rabi, or Isidore Rabi. And they realized, oops, the neutron has a magnetic moment. Well, basically, you see there is something hidden inside. So, what means is charged particles move inside, they create us this magnetic moment, which corresponds to some elementary magnetic field. Or we could say now a neutron, proton, electron, they are all building blocks, microscopic building blocks, Lego blocks, or elementary magnets. So, and if we have now many magnets, well, if one of them starts, there is an interaction energy between basically a magnetic field of one to the other. And if one starts to align, the other might want to align the same way, and then we build up. What we observe is not the only magnetic, or if they would be all randomly oriented, there would be none. At least from far away enough distance. If you come closer, you might observe there is locally something. Only if they start to point all in the same direction, we build up, we basically add them up to become a sizable magnetic field. So, if there's one, this is the so-called spin-spin interaction. Then they start building up. If you have pairs of them, they need to have a spin of 1. But their spin point, and therefore the magnetic moment points in the same direction. It turns out that in quantum mechanics that the magnetic moment is directly pointing along the orientation of the rotational axis of this intrinsic movement. Since we have loads of neutrons that can align, we get massive magnetic fields. In reality, that's then a bit more complicated. One has to take these Cooper pairs into consideration, and here it shall do it. By the way, the ferromagnet, what means if you have iron and then you put it into magnetic field, what will happen? The electrons now, first of all, they try to compensate this external and align all against. Then you take this permanent, they keep their orientation. And then you have a magnetization created. So it's the spin-spin alignment. We get here massive magnetic fields. There's loads of elementary ones, but we have a massive number of them. Well, in quantum mechanics, they have countable infinite. Basically, you can 1, 2, 3, 4, 5, but because there's so much that it's no chance really to count them in practical terms. But you could, but in practical terms, it's nonsense. So leaves us with the last question: how are the jets produced? And here is basically, we see here there are a lot of field lines going to a plane perpendicular. With the field line density is high. There is a lot of energy stored in this magnetic field. If we go out here, we see that only occasionally a field line is going through the same area. The field line density is much, much lower. And now charged particles want to be in regions. There is the energy content lower with low field line density. This is like a water particle wants to be at the bottom of the waterfall. Usually drops down and not up. For example, we use this technically with so-called magnetic bottles. So a particle, charged particle, that works even for atoms, for neutral atoms. It's served with anti-hydrogen. It's an anti-proton where positron, the antiparticle of the electron, is attached. Neutral, but there is still a magnetic rest interaction left, which is enough to trap it into such a magnetic bottle. And this team that does it is so-called Alpha Project. They succeeded doing so for months. Impressive. But usually with the charged particles it works even better. So if we have a high field line density, the particle will anyway gyrate around these field lines. That's the so-called Laurent Force, perpendicular to the field line. And now it wants to be in the region with lowest. So if it would gyrate here, it would become slower to the region of high field line density. It becomes slower and stop at some point, and then it starts being accelerated, gyrating back. But then if it is over the lowest field line density, it's basically now starting to feel a higher and higher field line density, and therefore slows down again until it's at some point stopped. But then it starts again, accelerated, go back. So it's trapped. Magnetic bottle. And then the second effect that we need here, so we have basically, where would this be realized? Well, we see that here's a region of high field line density, here of low. Then we overshoot and come again in this region of high field line density. And if there is no friction, this would go on forever. So stopped here, going back, accelerated, and then stopped, and going back, and so on. If there would be no friction. And here now the friction turns in so-called Bremsstrahlung. Every charge that is accelerated or deaccelerated emits radiation. Or we can also basically turn the argument around. It can also absorb radiation and then be accelerated. That is also possible. So if we have now an electron that is basically flying happily around until it flies past an atomic nucleus, which is positive charged and attracts him, there works then a force which basically bends the trajectory. It's accelerated towards this direction of the nucleus. Otherwise, the original trajectory would be continued. This leads to the emission of the so-called braking radiation, or acceleration, deceleration. Or for historical reason, we have the German name Bremsstrahlung. Brems is braking and Strahlung radiation. Okay. For example, the way the X-rays are made, you take electrons with a certain energy, accelerate them to a certain energy and hammer them on a metal plate. Then they get completely stopped, and because we can have now here every bending angle, the nature of the emitted radiation depends on the bending angle. We get now basically radiation out up to the maximum energy. That would be when the electron flies here basically against the nucleus and is completely stopped. Or hammers on and must be then even more accelerated. That's a good question how this happens. So, is it very close and then bend over? The ones that are stopped with the maximum energy. And then we get this what is called characteristic Bremsstrahlung, which would go on forever, but because usually this plate is extended, it starts absorbing radiation that has been produced in itself, and then it usually absorbs more low energy radiation. This means this stuff is basically filtered away. That's the way to make X-rays that you have, probably most of us have been exposed for medical reasons. That means if we have now our particles trapped in here and get accelerated here, it will emit radiation. It gets slower, for example. So that's some kind of friction. But along here, it gets, of course, also strongly accelerated. It also emits radiation. What you see here, it's so-called dipole radiation that would usually go perpendicular towards the direction where the acceleration and deceleration is. But there comes now some effect into game. That is from theory of relativity. That basically, if you're very fast or accelerate very fast, this what would go to the side is now basically bent more and more forward until it goes directly in the direction of motion. That's the so-called Lorentz boost. So all this radiation that is here produced is basically mostly, of course, in the very high field line densities, but the acceleration is highest. Is Lorentz boosted mostly to the forward. So we get here some kind of cone of radiation that is then also rotating with the other, with the rotation of the entire neutron star. So we can explain also this stuff. And from the typically observed energies that we have, the redshift by 2000 light years doesn't, at least if there is some redshift, this must have something to do with the system itself. And here comes now in that usually we would observe here X-rays, gamma rays. Later we talk about the gravitational redshift of photons. The photon, in order to escape from this gravitational sink, has to work against gravity. We talk about this later, therefore gets redshifted. So what here is emitted as X-rays and gamma rays is then gravitational redshifted. Because of this already very high gravity towards these radio waves that we have seen. And honestly, I'm rather exposed to radio waves than X-rays and gamma rays. So basically we can explain now also these jets. It's a question, will they rotate forever? No. So here measurement basically over a year measures this rotational frequency, and one sees that the period length increases. So for one rotation you need more and more time. What means the frequency decreases. But sometimes one sees that here this glitch, that it basically starts spinning faster. That can be now have two reasons. Either there was matter falling in and giving it again a push, like the poor daddy on the roundabout, or there was some kind of crack in the internal structure of the moment of inertia changed. So something like this can also happen. And the slowdown is caused by this emission of radiation. That means there's energy taken out of the entire system, therefore they slow down. Well, no. Another mechanism to take energy out of the system of binaries. This is quite interesting. There were in the Milky Way, there are at least two binaries of neutron stars. They were the super candidates for once in 200,000 years to observe gravitational waves. So here you see the solar masses, so 1.44 and the other 1.39 solar masses. They form basically some kind of common binary that rotate around each other. And if you remember this indirect proof for gravitational waves, that the periodicity of this system slowed down of the common rotation around the common center of revolution around the common center of gravity. So again, here is energy dissipated out of the system by gravitational waves. This was this proof, the commutative shift. So when the frequency, how often they basically go around each other, not frequency, the period length they take along to for one around this common center of gravity, that this is slowly but surely decreasing. Okay, but then for me very interesting was this observation of this crashing of these two neutron stars and the gamma ray burst that was associated. So basically you have these neutron stars, these massive magnetic fields, and when they come too close to each other, what will happen? Well, the nice thing is black holes are very, very stiff. Neutron stars might still be some fluid on the surface, so they are polarizable. They change a bit their shape, and so the signal is here completely different from what you get from black hole merger. If you think back to this lecture where we were talking about these black hole mergers, there was always this same shape, and now here the shape is different. Cool. This polarizability, for example, is very, very interesting for us. And there's especially the work, a name that would come to my mind, working in this interface between Nuclear and Astrophysics is Jorgen Pikariewicz at Florida State University. So if you're interested in about this merger stuff and what to learn from, they're very good. Well, at some point this intermediate state, and then we have here now two objects with a few protons, but loads of neutrons hitting. And the few protons are mostly on the surface. Our process side. So many people think now this is the R process, this rapid neutron capture side. So we get here this inspiraling, we get the cores merging, but a lot of the stuff is basically then emitted into space. Loads of neutrons around, very fast neutron capture processes. You come to extreme neutron-rich nuclei, or you go along this R process path. Well, and then towards the end, obviously, when you have all these reactions at the beginning, everything is very dense. When the central object is very likely a black hole, but on the surface, the light might then still be able to escape. Yet again, if a neutron star comes out, that means enough mass is going away to the side that we still stay below. And usually, we would also get another magnetic field, and what we get is obviously also a lot of electromagnetic interaction, and we get here these kilonovas. Then we get these gamma X-ray bursts also coming out. And of course the gravitational waves. But usually what happens is the residual mass is above this Oppenheimer-Volkoff limit, and we get a black hole. At this August 17, 2017, NASA's Fermi satellite, which is there for X-ray and gamma ray observations, has had this X-ray burst, gamma ray burst. These are events where suddenly we are hit by fluxes of light with extreme high energy, the photons, and extreme fluxes. These are called X-ray. If it's in the kilo electron volt regime of light, X-rays, if it goes beyond mega electron volt, giga electron volts, this is then called gamma rays, really hard radiation. And this happens quite often. Many of these origins we don't really have a clue. But back then, the Fermi satellite, these people directly triggered then the folks from LIGO and Virgo collaborations and said, check please, that looks like something has happened that might be a neutron star merger. In the signal, 2 seconds before, they found in the gravitational waves the signature. Why 2 seconds before? Well, there was obviously everything so dense that the light was trapped. Only then, when everything a bit cooled down, the light could escape. But then the gravitational waves and the light, that came then 2 seconds later because it was trapped, traveled was with the speed of light, and yeah, so bang. They basically said, okay, then they triggered everything they could. They triggered everything. First of all, you narrow down the search region where could it have happened. And then in total there were 16 observatory satellites to go investigate the object. And the resulting publication was a physical review letter, which is typically the scientific content is limited to 4 pages. Occasionally, things like this, the editors might say, okay, you get a half extra page. This one had 105 pages. Because 101 pages were there for all the author names and their affiliation, what means the institutions they work for. So if you print ever this paper, go for just the last couple of pages. Interestingly, you also find UWS because they are at LIGO. This is about half to a third to half of the worldwide astronomers society. So if you print them in the standard paper, 12-inch aerial, 12-point aerial, or whatever this is, times Roman, with the affiliations, 100 pages. Just names and institutions. Okay, enough of this stuff. So first of all, for us, it's of course this our processing scenario. So the nova and that it makes, but then Neutron Star merger, that in the inspiraling, there's a lot of stuff coming out, and with it, hydrogen mostly on the surface, or a few heavier nuclei. And this is now bombarded also with the neutrons that also come out. Loads of neutrons. And then, so hopefully one then can explain this this elemental abundancy, where you see here the mass number and here the fraction of the mass that is there. So it's a promising scenario for this, that we have this neutron-rich stuff that produces then go up here, and maybe uranium and the heavier elements. But how this was detected, please have a look here at this video the expert is telling you about. And then after this video, let's say again, take a bit of a break, go around. And then we talk a bit more about these neutron star mergers, what is produced, and then go for the magnetars. Well, what was quite interesting, Virgo and LIGO have seen the event. They nicely also got the waveform, or could say, okay, this must be two neutron stars merging. Virgo didn't have. And you will see here, basically, how anyway Virgo still could contribute, because we knew now it must have come in these two, stop share, in these two arms, in an angle which corresponds to a blind spot. It's not the best you can have, but at least you can exclude these directions. And then you can narrow down. Together with LIGO, these two observations, one could narrow down to an area with about 60 galaxies. And then people were starting scanning, and the fourth or fifth galaxy they scanned. Oh, there it is. So 2 hours after the event, it was basically identified where. And then the 60 observatories zoomed in. Okay, so after this, we are quickly going to magnetars. What are magnetars? And then we go to black holes. See you then, hopefully, after you have stretched your legs and refreshed a bit your mind.